Good afternoon. So today we'll continue determinants, NCERT section 4.6, and we do some example 16, 17, and 18. Okay. So in today class we see how we can use determinants and matrices to solve system of linear equation. So to solve system of linear equation of 2 or 3 variable and checking for consistency of the system of linear equation, it means system has a solution or it has no solution. We use determinants and matrices. For a system of equation Ax is equal to B, here A is a matrix, X is also a matrix of variables, and B is a matrix of constants. A system of equation is consistent if it has one or more solution. So if a system of equation has a solution, then it is called consistent system. If a system of equation has no solution, then the system is called inconsistent. Okay, so a system of linear equation in n variable can be represented as a matrix equation. We know that we can represent system of linear equation in matrix form, and that form is Ax is equal to B. And we can solve this system of equation by inverse of a matrix. We already know how we can find inverse of a matrix. So consider the system A1x plus B1y plus C1z is equal to D1. A2x plus B2y plus C2z equal to D2. A3x plus B3y plus C3z equal to D3. So here there are three linear equation, system of equation with three variable x, y, and z. Okay. So then the system of equation can be written as Ax is equal to B, where the matrix A is matrix of coefficients. The first column represent coefficient of x, second one is coefficient of y, then coefficient of z. The X matrix represent the matrix of variables x, y, and z, and B matrix represent the all constant D1, D2, and D3. Okay, so that's how we can represent a system of equation in matrix form. If we multiply, as we see the equation Ax is equal to B, so when we multiply A with X and then equate with B, we get exactly the same system of linear equation. Okay. So we know what is singular matrix and non-singular matrix. So A is non-singular, it means determinant of A is not equal to 0. So in this case, A inverse exists. A inverse exists only if determinant of A is not equal to 0. Then pre-multiply the equation Ax is equal to B by A inverse. So we get, when we multiply A inverse Ax is equal to A inverse B, we write A inverse A into X is equal to A inverse B, and we know A inverse A is identity matrix. So we just write X. So X is equal to A inverse B, and that is the value of variable. Okay. So the first condition is A must be a non-singular matrix. That means determinant is non-zero. Then A inverse exists, and if A inverse exists, then by using this formula, that is X equal to A inverse B, we can calculate the variables of system of linear equation. Okay. So the solution is unique and given by X is equal to A inverse B, where A inverse can be found as 1 by determinant of A into adjoint of A. So this is your first criteria to have a unique solution for a system of linear equation. If determinant of A is non-zero, then A inverse exists, and if A inverse exists, then we calculate X by formula A inverse B, where A inverse is 1 by determinant of A into adjoint of A, and in this case system of equation has a solution, so system is consistent and it has a unique solution given by X is equal to A inverse B. Second case, if determinant of A is equal to 0, that means A is singular. Then now we calculate adjoint of A into matrix B. So again two cases arise. If adjoint of A into B is not equal to 0 and if adjoint of A into B is equal to 0. So first case is determinant of A is non-zero. Then system is consistent as a unique solution. Now in second case, if determinant of A is 0, then we calculate adjoint of A into B. And now there is subcase of the case 2. That is, if adjoint of B is not equal to 0. In this case, system is inconsistent. So, if adjoint of A into B we calculate and it becomes non-equal to 0, then system is inconsistent. In this case, system has no solution. Okay. The reason is A into adjoint of A. We know by the formula it can be written as determinant of A into I. And in this case, determinant of A is 0. So it becomes 0. Now, multiply AX is equal to B by adjoint of A gives adjoint of A into AX is equal to adjoint of A into B. Okay, we just multiply adjoint of A into this equation. So adjoint of A into A from above, we get determinant of A into X. Okay, equal to adjoint of A into B. Now, determinant of A is 0. So it becomes 0. 0 matrix is equal to adjoint of A into B. But in this case, we already consider it as adjoint of A into B is not equal to 0. But here is a contradiction. We get is equal to 0, which contradict. So, system of equation has no solution. Okay. Subcase 2b. If adjoint of A into B is equal to 0, then system may be either consistent or inconsistent. In this case, might be possible that system of equation has a solution or no solution. If consistent, it has infinitely many solutions. Okay, so if in this case system of equation exists solution, then it has infinitely many solutions. If inconsistent, it has no solution. Okay. So we can summarize it as, if determinant of A is not equal to 0, then system of equation is consistent and has unique solution, and it is given as X is equal to A inverse B. Second case, if determinant of A is equal to 0, then A inverse doesn't exist. In this case, we calculate adjoint of A into B, and if adjoint of A into B is not equal to 0, that is your second case, subcase of second not equal to 0, then system is inconsistent and no solution. And in the third column row, you can say adjoint of A into B if is equal to 0, then system is consistent or inconsistent. But if it is consistent, then it has infinitely many solutions. Okay. So here example 16, that is, solve the system of equation 2x plus 5y is equal to 1, 3x plus 2y is equal to 7. Now we use determinants and matrix to solve this example. Okay. So you, using the theory, try to solve this question. We need to solve system of equation 2x plus 5y is equal to 1, 3x plus 2y is equal to 7. So at first, we write this equation in matrix form. The form is Ax is equal to B, where A is matrix of coefficients. So 2, 5, 3, 2. Okay. And the variables are x and y, that is matrix X. X is equal to xy. And for matrix B, 1 and 7. Okay. Now, we calculate determinant of A. So, to know if this system equation has a solution or no solution, at first we have to calculate determinant of A. If it is equal to 0, then we go to subcase 2A and 2B. But here, determinant of A is minus 11, that is not equal to 0, that is your case 1. So, the system has a unique solution and it is consistent. Okay. So, if determinant of A is not equal to 0, A is non-singular, the system is consistent, and it has a unique solution given by x is equal to A inverse B, where A inverse is equal to 1 by determinant of A adjoint of A. So in the first case, at first we have to convert the given system linear equation to matrix form, and then we have to calculate determinant of A. If it is not equal to 0, then we can say system is consistent and it has a unique solution which is given by x is equal to A inverse B. So for this formula, now we have to calculate the value of A inverse. And for that, we have to calculate adjoint of A. Hence, A is non-singular matrix and so has a unique solution. For a square matrix of order 2, let a square matrix of order 2 with elements A11, A12, A21, A22. Now we try to find the value of A inverse. Then adjoint of A can also be obtained by interchanging A11 and A22 and by changing sign of A12 and A21. So we can directdirectly find the adjoint of A in case of square matrix of order 2. As here, the matrix is A11, A12, A21, A22. So to get adjoint of A, we just need to interchange the position of A11, A12. So now, in position of A11, there is A22, and in place of A11, there is A22, and in place of A22, there is A11. Okay, we just interchanging A11 and A22 and changing sign of A12 and A21. So in place of A12, here minus A12, and in place of A21, here is minus A to 1. And this matrix is adjoint of A. So we can directly find the adjoint of A in case of matrix of order 2. Then we get adjoint of A is equal to 2 minus 5 minus 3, 2. To get adjoint of A, interchanging 2 and position 2 and 2, that is same, and in place of 5 we place minus 5, and for 3 minus 3. We get adjoint of A. Now we have to calculate A inverse, and the formula for A inverse is equal to 1 by determinant of A into adjoint of A, and the value of determinant of A is minus 11. So A inverse is equal to 1 by determinant of A, that is minus 11, into adjoint of A. So now we have a value of A inverse, and the formula to get the solution of system of linear equation is x is equal to A inverse B. So just substitute back the value of A inverse. So we get x is equal to A inverse, that is minus 1 by 11, matrix 2 minus 5 minus 3, 2, into matrix B. Matrix B is 1, 7. This is a matrix multiplication. Multiply the matrix. So xy, in place of x, we write the matrix of x, that is xy is equal to minus 1 by 11, and multiply the matrix 2 minus 5 minus 3, 2, into matrix 1, 7. So to multiply, how we multiply? We just take first row, that is 2 and minus 5, and multiply with first column. So 2 into 1 plus minus 5 into 7. That's how we multiply in matrix. So 2 into 1 plus minus 5 into 7. That is 2 into minus 35. That is minus 33. And then take second row. That is minus 3 into. So multiply second row with this first column. So minus 3 into 1 plus 2 into 7. So minus 3 into 1, that is minus 3. And 2 into 7 is 14. So you get minus 3 plus 14, that is 11. So that's how we multiply in matrix. Okay. So we get minus 1 by 11 matrix minus 33, 11. Okay. Now we take this 11 minus 1 by 11 into under the matrix. So at first it divide minus 33. So when we divide minus 33 by minus 11, we get 3, and 11 by minus 11, that is minus 1. Hence, just equate the value x is equal to 3 and y is equal to minus 1. That's how we can find the value of the variable using matrix and determinant. Next example is solve the following system of equation by matrix method. Given system of equation is 3x minus 2y plus 3z equal to 8, 2x plus y minus z equal to 1, 4x minus 3y plus 2z equal to 4. So here is three linear equation system of with three variables. So at first convert it into matrix form. Write the matrix A, then calculate determinant of A, and according to the determinant value, it is either 0 or non-zero. If it is 0, there is two subcases, and if it is non-zero, then we calculate A inverse, and by using the formula x is equal to A inverse B, we find the variables. So try. So to solve this given system of linear equation using the matrix method, so the given system equation is 3x minus 2y plus 3z equal to 8, 2x plus y minus z equal to 1, 4x minus 3y plus 2z equal to 4. So at first, write the system equation in matrix form. That is Ax is equal to B. So here the matrix A is matrix of coefficients. Just take the coefficients 3 minus 2, 3, 2, 1 minus 1, 4 minus 3, 2. Just take the coefficient from the system of linear equation. Okay. And the matrix X is matrix of variables. So here three variables X, Y, and Z. And matrix B is the constants are 8, 1, and 4. Okay. So now we write this system of equation into a matrix form. So in the second step, we now calculate determinant of A. So to calculate determinant of A, we have to expand it along any row or column. So we expand along the first row. So when we expand the matrix A along the first row, we get 3 into determinant of matrix of order 2 cross 2, that is obtained by just cancelling first row and first column. Minus 2, 2 minus 1, 4, 2 plus 3 into 2, 1, 4 minus 3. Now just simplify it. Calculate determinant of this all 3 2 cross 2 matrix by multiplying the its product of diagonal element minus product of off diagonal element. So 2 into 1 minus 1 into minus 3 plus 2 into 2 into 2 minus 1 into 4 plus 3 2 into minus 3 minus 1 into 4. So when we simplify, we get determinant of A is equal to minus 17. Now determinant is minus 17, that is non-zero value. So if we get a determinant that is non-zero, the matrix A is non-singular. So A inverse exists. So we can find solution, unique solution, system has unique solution, and it is consistent. Okay. Now we know as determinant is non-zero, so A inverse exists and we can calculate the solution for the system of linear equation. And for that, we at first we have to calculate A inverse. And to calculate A inverse, we have to calculate adjoint of A. And to calculate adjoint of A, that is transpose of matrix of cofactor. So now we have to calculate the cofactor matrix of A. The cofactor Aij is given by minus 1 the power I plus j mij, where this mij is minor of the element aij. So to calculate cofactor matrix, we have to calculate cofactor aij for each element on that matrix, and that is given by minus 1 the power I plus j into minor of that element. Okay. So for the first element, the cofactor a11 is minus 1 the power 1 plus 1, determinant minor m11, and minor is calculated by, if we have to calculate minor of first element a11, then just delete the first row and first column, and the matrix we obtained by deleting the first row and first column, that the determinant of that matrix is your minor, and that is your matrix 1 minus 1 minus 3 2. So now calculate determinant. So 2 minus 3, it become minus 1. That is cofactor of the element a11. In a similar way, we calculate cofactor for the element a12. So it become minus 1 the power 1 plus 2, and then into minor of 1 2. Minor of 1 2 is on the matrix A, cancel first row and second column. The matrix you obtain, that is this matrix 2 minus 1 4 2, calculate determinant. Determinant is calculated as multiply the product of diagonal element minus product of off diagonal element. So cofactor A12 is minus 8. In the same way, we calculate A13, that is minus 10. A21, that is minus 5. A22, minus 6. A23, that is 1. A31 is minus 1. A32 is 9. A33 is 7. To calculate cofactor, just multiply minus 1 the power I plus j. Index value for A33, it's 3 plus 3. And then multiply with minor of A33. And minor of A33 is obtained by, if for A33 element, just cancel third row and third column. We get a matrix of order 2 cross 2 on that matrix. And determinant of that 2 cross 2 matrix is your minor. Okay, so that's how we calculate cofactor for all the elements. The cofactor matrix C is equal to A11, A12, capital A11, capital A12, capital A13. Write all the values of the cofactor. A21, A22, A23. Okay, so this is your cofactor matrix. So at first we calculate cofactor matrix and then write the cofactor matrix. Okay, so to calculate the adjoint of A is given by transpose of cofactor matrix. So just transpose the cofactor matrix. So the row become column. So the first row, that is minus 1, minus 8, minus 10, become the first column of the adjoint of A, that is minus 1, minus 8, minus 10. In the similar way, minus 5, minus 6, minus 1 of the second row of the cofactor matrix become second column of adjoint of A. Okay, so that's how we find adjoint of A. Now we have a matrix adjoint of A. Now we can calculate inverse of A. So A inverse is given by 1 by determinant of A into adjoint of A. And we already calculated adjoint of A and determinant of A. Then determinant of A is minus 17, and adjoint of A is minus 1, minus 5, minus 1, minus 8, minus 6, 9, minus 10, 1 and 7. So to calculate inverse of A, at first we find cofactor, then transpose it to get adjoint of A, and then by using the formula we get inverse of A. Now we have a value of inverse of A. So we can use this formula to get the variables, that is x is equal to A inverse B. So x is equal to 1 by minus 17 and the matrix minus 1, minus 5, minus 1, minus 8, minus 6, 9, minus 10, 1 and 7. It is a value of A inverse. And for the B, 8, 1 and 4. Okay, so we have to multiply this both matrix. So when we multiply, take the first row and there is only one column. So multiply minus 1 with 8 plus minus 5 into 1 plus minus 1 into 4. So that's how we multiply the matrices. Okay. First, now take the first row, the second row, and multiply with the first column of the matrix B. So minus 8 into 8, minus 6 into 1, plus 9 into 4. Third row, minus 10 into 8, multiply with the column. So 1 into 1, plus 7 into 4. When we simplify, we get minus 1 by 17 is equal into minus 17, minus 34, minus 15, 51. Now multiply each element by 1 by minus 17. So when we multiply each element by minus 17, we get 1, 2 and 3. And that is the value of the variables. X is equal to 1, y is equal to 2 and z is equal to 3. Okay, so that's how we solve system of linear equation. Next example is the sum of three number is 6. Clear? First statement is we have three numbers and the sum of three number is 6. If we multiply third number by 3 and add second number to it, we get 11. Second statement. Third, by adding first and third element, we get double of second element. Third statement, represent it algebraically and find the number using matrix method. So, this is also a system of linear equation, but in a statement form. At first, you have to convert into a equations by using this statement like sum of three number is 6. And then using matrix method, try to solve. So let first, second, and third number be denoted as x, y, and z. So we have three numbers. Now we convert into a system of linear equation by using the statement on a question. Then according to given condition, we have the sum of three number is 6. It means x plus y plus z is equal to 6. So we get a first equation, first linear equation. Now, second statement is if we multiply third number by 3 and add second number to it, we get 11. So it means third number is z. So multiply third number with 3. So 3z and add second number to it. So y plus 3z is equal to 11. Second condition. So we get second linear equation. Now third statement. By adding first and third number. So first number is x, third number is y. So x plus y, we get double of second number. Second number is y. So first and third, that is x plus z, we get double of second number, that is double of y. So x plus z is equal to 2y. That is x minus 2y plus z equal to 0. We get three linear equation, system of three linear equation. The given system equation is x plus y plus z equal to 6, 0 into x plus y plus 3z equal to 11, x minus 2y plus z equal to 0. First task is complete. Now we have a system linear equation. Now we write in the second step into matrix form. So matrix form is Ax is equal to B, where matrix A is matrix of coefficient 1, 1, 1, 0, 1, 3, 1, minus 2, 1. The matrix X is equal to X, Y, Z, and B is equal to 6, 11, 0. You write down the matrix A. We use this matrix A to find the cofactor value and adjoint A to get A inverse. Okay, so just write down the matrix A. Now, calculate the determinant of A. Second step is complete. We write in the matrix form. Now, in third step, we calculate determinant of A. Determinant of A is equal to expand along the first column. So when we expand along the first column, we get determinant of A, that is 1 into 1, 3 minus 2, 1, minus 0, 1, 1 minus 2, 1, plus 1, 1, 1, 1, 3. So when we calculate determinant of all these three 2 cross 2 matrices, we get determinant of A is equal to 9, and that is a non-zero value. So we get a determinant that is non-zero value. So the matrix A is non-singular and thus A inverse exists. This means system equation has a unique solution. Okay, so in this question, at first we convert the given line into system linear equation. So there is given sum of three number. So we take three number as x, y, and z. So three number are x, y, and z. The first statement is sum of three number is 6. So x plus y plus z is equal to 6. That is your equation number 1. So now we get first system, linear equation. The second line, if we multiply third number by 3, third number is z. We multiply by 3. So 3z and add second number to it. Second number is y. So y plus 3z, we get 11. So second equation is y plus 3z equal to 11. That's your second equation, linear equation. Third line is by adding first and third number. First number is x and third number is z. So by adding first and third number, that is x plus z, we get double of the second number. Double of second number is y. So x plus z is equal to 2y. So we have three linear equation. First x plus y plus z equal to 6, and then y plus 3z equal to 11, and the third is x plus z is equal to 2y. Okay, so we get three system of linear equation by using this three statement. Okay. You get recorded in class in recorded format. So now we have three system linear equation. So at first we write in a matrix form, that is Ax is equal to B, and the matrix A is coefficient matrix. So we get a coefficient matrix. And when we get a matrix A, then we calculate determinant of A. And if determinant of A as we calculated is 9, as is non-zero, so system is A is non-singular, then system is consistent as has a unique solution. And as determinant of A is non-zero, A inverse exists. So to get the inverse of A, at first we calculate cofactor matrix of A. The cofactor A is given by minus 1 the power I plus j into mij, where mij is minor of the element aij. Okay. So now we calculate cofactor matrix, and for that we calculate cofactor aij, capital Aij, for each element aij, and that is calculated by just multiply minus 1 the power I plus j with minor aij, and minor is obtained by if there is a matrix. If there is a matrix and we have to calculate minor for first element a11, then just delete the first row and first column, we get a matrix of order 2 cross 2, and when we calculate determinant of that matrix, you get minor 1. Okay. So now we calculate cofactor a11, that is minus 1 the power I plus j, 1 plus 1, 1 3 minus 2 1. So when we calculate determinant of this, we get 1 into 1 minus minus 6, that is 7. Cofactor a12, that is minus 1 the power 1 plus 2, determinant of 0 3 1 1, that is 3. In similar way, we calculate cofactor a13, that is minus 1, a21, that is minus 3, a22, that is 0, a23, that is 3. The cofactor value of a31 is 2, A32 is -3 and A33 is 1. So now we calculate cofactor for each element. So we write cofactor matrix. And the cofactor matrix C is 7, 3, -1, -3, 0, 3, 2, -3, 1. To calculate the adjoint of A, we just transpose the cofactor matrix. So when we transpose the cofactor matrix, the rows of cofactor matrix become column for the adjoint of A. So we get 7, 3, -1. The row -3, 0, 3 become column 2, -3, 0, 3. And the column third row 2, -3, 1 become 2, -3, 1. Now we find the inverse of A, and the formula for inverse of A is 1 by determinant of A into adjoint of A. Determinant of A is 9, so 1 by 9 into adjoint of A, that is 7, -3, 2, 3, 0, -3, -1, 3, 1. So now we solve for x using, now we have a value of inverse of A. So by using inverse of A, we calculate all the variable by using the formula x is equal to A inverse B. So x is equal to 1 by 9, then 7, -3, 2, 3, 0, -3, -1, 3, 1, and the matrix B, that is 6, 11, 0. Now we multiply the matrix. So to multiply, take the first row and multiply with the column. So 7 into 6 plus -1 into 11 plus 2 into 0. Then for second row, 3 into 6 plus 0 into 11 plus -3 into 0. Then -1 into 6 plus 3 into 11 plus 1 into 0. So when we simplify, we get x is equal to 1 by 9 into matrix 9, 18, and 27. Now multiply each element by 1 by 9. So x is equal to 9 by 9, that is 1, 18 by 9, that is 2, and 27 by 9 is 3. So x, y, z is equal to 1, 2, and 3. So the value of x is 1, value of y is 2, and z is equal to 3. Okay. Example 19 is, use this product 1, -1, 2, the matrix 1, -2, 0, 2, -3, 3, -2, 4 into matrix -2, 0, 1, 9, 2, -3, 6, 1, -2. Solve the system of equation this. Now we have to use the product of this two matrix to find the solution for system of linear equation. So just try. We need to solve the system equation using product of this two matrix. So consider the product. So to multiply this both matrix, we take first row 1, -1, and 2 and multiply with the first column of the second matrix. So 1 minus 2, that is -2, -1 into 9, that is -9, 2 into 6, that is 12. And then the first row with second column. So 1 into 0, that is 0, -1 to 2, that is -2, and 2 into 1, that is 2. And then the first row with the last column. So 1 into 1 plus minus into 3, that is plus 3, 2 into minus 2, that is minus 4. Now take the second row, 0, 2 and minus 3 and multiply with each column. So 0 into minus 2, that is 0, plus 18 minus 18. Then multiply with second column, 0 into 0, 0, 2 into 2, 4, minus 3 into 1, minus 3. And multiply with the third column. So it becomes 0 into 1, 0, 2 into minus 3, that is minus 6. And minus 3 into minus 2 is 6. Take the third row and multiply with the first column. So 3 into minus 2, minus 6, minus 2 into 9, minus 18 plus 24. Then multiply the third row with second column and then third column. So that's how we multiply the matrices. And simplify, we get 1, 0, 1, 0, 0, 1, 0, 0, 0, 1. And that is your identity matrix. So if as we get identity matrix, so the product of this matrix are inverse of each other. The first matrix inverse of second matrix and second matrix inverse of first matrix. Okay. If A into B is equal to Y for any two matrix A and B, we know that as A into A inverse is equal to I, identity matrix, so matrix B is inverse of A. Hence, the inverse for this matrix is minus 2, 0, 1, 9, 2, minus 3, 6, 1, minus 2. Now given system of equation can be written in matrix form. So we write the given system equation into matrix form. So we write it as matrix A into X is equal to B. So the matrix A is coefficient matrix. So take 1, minus 1, 2, 0, 2, minus 3, 3, minus 2, 4. And then matrix of variable X, Y, Z. And the last one is matrix of constants 1, 1, 2. So this matrix A is same as the matrix was given in the product, the first matrix. So we already know what is the inverse for this matrix by using the product, and it is identity. So we write it as X is equal to A inverse B, and the value of A inverse is 201, 923, 612 into the matrix B, that is 112. So now we don't need to calculate the inverse of A by using the product. We already have the value of A inverse. So when we multiply, we get minus 2 plus 0 plus 2, 9 plus 2 minus 6, and the third row 9, 6 plus 1 minus 4. That is 0, 5, and 3. Hence, X is equal to 0, Y is equal to 5, and Z equal to 3. Okay, so in summary, determinant is a unique number associated with a square matrix. And we can expand along any row column in which there is most 0 to simplify the expression. Determinant of A, some property determinant of A is determinant of transpose of A. And if we just change the rows in a determinant, the determinant value is changed by just sign. If there is two identical rows in a matrix, then determinant of A is 0. Now change the first row by multiply a constant, then the determinant is just multiplied by K. And if we change the row Ri with Ri plus Krj, then determinant of A is unchanged. And we can calculate area of triangle using this formula and by using determinant of matrix x1, y1, 1, x2, y2, 1, x3, y3, 1. Okay. What is cofactor and adjoint? Cofactor is Aij is equal to minus 1 to the power I plus j into minor ij. We can calculate for each element. First, we calculate minor ij, and when we multiply with minus 1 to the power I plus j, we have the value of cofactor Aij. And by using the all value of cofactor, we construct a cofactor matrix. And when we take the transpose of cofactor matrix, we get adjoint of Inverse of a matrix. Inverse of matrix exists only if determinant of A is not equal to 0. Then A inverse is equal to 1 by determinant of A into adjoint of A. So to calculate inverse of a matrix, at first we have to check is determinant of A is 0 or non-zero. If it is non-zero, then calculate cofactor matrix, take it transpose and calculate adjoint of A. And then A inverse is equal to 1 by determinant of A into adjoint of A. And to solve linear equation Ax is equal to B, if determinant of A is not equal to 0, then it has unique solution and x is equal to A inverse B. And if determinant is equal to 0, then we have to check adjoint of A into B to determine system is consistent or not. Okay, so in today's class, we use matrix and determinant to solve system of linear equation. So now if you have any doubt, please ask.